Your CI pipeline stalls. Your bots start hammering GitHub's API every few seconds hoping it comes back. Okay, picture this for a second. You're sitting at your desk, eyes locked on your deployment monitor, and everything just stops. The dashboard goes completely red. Your automated systems start panicking, desperately firing off requests into the void, waiting for a response that just isn't coming. It is a literally terrifying moment for any engineering team.
And then, those stressful minutes turn into hours. 7 hours and 47 minutes, to be exact. That is the staggering duration of the GitHub outage that went down on August 17, 2026. For almost an entire working day, millions of developers and countless automated workflows were just paralyzed. The sheer scale of this downtime, the massive pain it caused across the global software supply chain, it was unprecedented. But you know what? The reason it lasted this long is the real story here.
Okay, let's dive into this. We aren't just going to do a quick news recap today. No, we are going to explain this in depth. We're doing a full systems autopsy. We're going to decode the anatomy of a retry storm, using GitHub's own official postmortem as our map to figure out exactly why a totally standard infrastructure hiccup mutated into nearly 8 hours of catastrophic downtime. Here is the agenda for today's explainer. 1. The 8-hour outage. 2. Not a normal capacity failure. 3. Anatomy of a retry storm. 4. The jammed phone line. 5. Fixing your retry logic. And finally 6. The risk you inherited.
Section 1. The 8-hour outage. Symptoms of a system in distress.
Let's ground ourselves in the raw events of that day. On August 17, 2026, it wasn't just, a single feature going offline. GitHub's core services, the website, the API, actions, issues, pull requests, even Copilot, they all universally degraded at the exact same time. If we look at the error rates, the main site and API spiked to roughly 20%, but repository download error rates, those hit a staggering 40%. This is totally catastrophic because it paralyzes CI and CD pipelines. Think about it. If your automated deployment can't pull code, it blocks every single workflow from even starting. And remember, this wasn't an isolated string of bad luck. This was GitHub's 5th notable incident in just 3 weeks. The system was clearly under immense distress. So what was the initial spark? Well, according to GitHub's official postmortem from August 20th, the outage began when traffic hit a massive new peak, and a critical infrastructure component in their central US data center just simply failed to scale with it. It was a classic capacity failure. The pipe literally wasn't big enough for the water trying to rush through it. But here's the thing. A capacity failure alone doesn't explain an 8-hour nightmare.
Section 2. Not a normal capacity failure. Diagnosing the true cause.
Now what's really interesting here is that if this was just a simple capacity issue, it would have been solved like a typical capacity issue, right? Let's look at a direct comparison. During a different incident back on July 29th, an internal service ran out of memory, GitHub simply scaled it up, and boom, the issue was resolved fast. Textbook. But the August 17th outage? That started as a capacity hit and immediately spiraled into a cascading failure, where starved resources led to thread pool exhaustion, keeping the whole system down for an extended 8-hour recovery. The sheer duration proves this wasn't just a basic under-provisioning issue. Something else was actively keeping the system down.
Section 3. Anatomy of a retry storm. How clients extended the outage.
So here is where we need to shift our focus away from GitHub's servers and look at the client-side behavior. We have to look at what the users, and more specifically, the automated tools the users deployed, were doing while GitHub was frantically trying to fix the problem. The culprit here is an absolute beast called retry amplification. This is a cascading failure mode, where automated clients, your bots, your CI pipelines, your AI agents, aggressively and repeatedly attempt to reconnect to a struggling server. By doing this, they artificially multiply the load and totally prevent recovery. Essentially, well-meaning developer bots were launching a massive, self-inflicted DDoS attack right on GitHub. Let's walk through this vicious cycle step by step to really explain it in depth. Step 1. The initial server error occurs. That central US data center hits its capacity limit. Step 2. Because they are programmed to be resilient, automated bots instantly see the error and retry the connection. Step 3. Because thousands and thousands of bots are doing this simultaneously, the server load artificially spikes exponentially higher than the original traffic peak. And finally, step 4, GitHub's engineers try to spin up recovery servers, but those new servers are instantly hammered by the artificial spike, causing them to crash completely during the recovery attempt. The system physically cannot boot up because it's being suffocated the very second it turns on. Section 4. The
the jammed phone line, visualizing the bottleneck.
Now, if that technical cycle feels a bit abstract, this metaphor brilliantly illustrates it. Think of a jammed phone line during a major event, like, trying to buy tickets to a huge concert. If everyone hangs up and redials the number every 2 seconds, the phone network switches get completely overwhelmed. The line jams even harder. During this outage, CI bots, webhook consumers, and automated agents acted exactly like panicked callers redialing nonstop. They didn't care that the system was down. Their code just told them to keep trying, over and over.
Conversely, if callers space out their retries, if they wait a minute, then maybe 5 minutes, then 10, the underlying system gets the breathing room it desperately needs to clear the backlog and start routing calls successfully again. A server is literally no different. It physically cannot process a massive backlog of new requests while simultaneously trying to rebuild its underlying infrastructure. It needs quiet.
And I want to be super clear here. This isn't just theory. This isn't just our armchair opinion of what might have happened. GitHub's official postmortem directly blamed client-side retry loops for compounding the disaster. That is the official root cause finding published directly by their own engineering team. The very tools designed to keep developers productive were the exact things keeping the platform offline. Crazy, right?
Section 5. Fixing your retry logic, the prescription.
So we've diagnosed the problem, but understanding the disease isn't enough. Now we need the cure. It's time to transition from diagnosing the issue to equipping you with the exact engineering practices you need to implement this week. In their postmortem, GitHub's primary fix for this incident was to implement consistent retry limits and retry budgets. And the absolutely crucial point is that they prioritize this over adding more than 3 million CPU cores to their capacity. Before they threw more metal at the problem, they realized they had to fix the client behavior. They're explicitly telling every single team integrating with their API, your retry logic is part of the problem.
So what does fixing it actually look like for you? Here are 3 highly actionable technical solutions. Number 1, implement exponential backoff. Please don't retry every 2 seconds. Retry after 2 seconds, then 4, then 8, then 16. Give the server time to breathe. Number 2, add jitter. If you only use exponential backoff, 10,000 bots might still wait exactly 8 seconds and retry at the exact same millisecond, causing what engineers call a thundering herd problem. Jitter adds randomness to the timer, spacing out those requests perfectly so they don't arrive in a huge synchronized wave. And number 3, cap your total retry attempts. Know when to just give up and fail gracefully. If you run webhooks, CI pipelines, or AI agents, you need to check these configurations in your codebase, like today.
Section 6. The risk you inherited. A systemic prognosis.
As we wrap up, we really need to frame this entire postmortem as a broader philosophical lesson in modern systems architecture. Here is the absolute bottom line, and it is absolutely crucial. A vendor outage becomes your outage the moment your retry logic decides to fight it instead of wait it out. When GitHub goes down, sure, that's GitHub's problem. But when your poorly configured bots hammer a recovering API, extending a 2-hour blip into an 8-hour catastrophe, well, your reliability budget is now tied directly to your own flawed retry logic. You essentially become complicit in the downtime.
Which leaves us with a final, pretty provocative thought. If your own service has downstream clients retrying against you, is your retry storm risk inherited from systems you don't even control? Think about your own architecture right now. Are your users ready to accidentally DDoS you the next time you have a minor capacity hiccup? It's a massive question and one every engineering team needs to seriously answer. As a quick reminder, this explainer is for educational purposes only and discusses GitHub's publicly disclosed reports. Always consult a qualified engineer for your specific systems. Thanks for exploring the anatomy of a retry storm with me today, and make sure your systems are architected to heal, not to harm. Catch you next time.